So, I don't feel that we officially talked about conservation of mechanical energy, which may be part of why the homework was a problem for some people. Okay, so let's get through these notes and these examples today, and then if you need to turn in the homework tomorrow, like I said, that's fine. Okay, so the first thing we want to talk about is mechanical energy. And some of this we went over when we were getting ready to do the energy of a tossed ball lab. Okay, and so we said that Emac was equal to what? Anybody remember? Well, not exactly delta K plus delta U, but it's the kinetic energy plus the potential energy at any point. Okay, which probably would have been helpful in your homework, because then what we're going to talk about is that this total amount of energy here, this total amount of mechanical energy, isn't going to change between points when you're doing a problem. Okay, so it's important that when we talk about conserving energy, that we only apply this to certain situations. Okay, so there are kind of some conditions for what we're about to do. And the first thing is that only conservative forces create the transfers of energy. Which is okay, because both the gravitational force and the elastic force are both conservative forces. And remember, conservative means that when I move the object back to its original configuration, I get back whatever energy I expended in putting it there. So if I stretch the spring out, when the spring goes back to where it started, the same amount of energy is transferred back to the system as I took out in the first place. Okay? And the second condition that we need to meet here is that the system is closed and isolated. And I'll tell you what that means in a minute. And we're going to find that most of our conservation laws involve systems that are closed and isolated. So closed means no mass leaves or enters the system. So I can't magically double the size of the bob on the end of my pendulum and expect energy to be conserved. And isolated means no external forces. So I'm not talking about friction. If we're going to use the gravitational force, we need to make sure that we include the Earth as part of the system, which we do, and it's okay. All right. Okay, we good? We got it? Okay, so for conservative forces, we know that delta K is equal to the amount of work done, but we also know that delta U is equal to the negative of the amount of the work done. So that tells us that delta K is equal to negative delta U. so that the energy that's lost from kinetic energy is gained by potential energy and the other way around. So I could say that, for instance, K2 minus K1, if positions 1 and 2 are where my object is moving between, is going to be negative U2 minus U1. And then if I put all the 2's on one side and all the 1's on the other, I've got K2 plus U2 is going to be equal to K1 plus U1, or my mechanical energy at one position is equal to the mechanical energy in the other position. So even though the energy can flow back and forth between kinetic energy and different kinds of potential energy, the total mechanical energy of the system is going to stay the same. So my final statement here for the principle of energy conservation is that the change in mechanical energy is going to be equal to the change in kinetic energy plus the change in potential energy, but that's got to sum to 0. Okay? Although I think writing it this way is probably a lot more useful when we're solving problems. Now, this actually puts us ahead of where we were with Newton's laws. It puts us ahead of where we were with Chapter 2 equations, because now I can compare two positions and know something about the velocity associated with that position, or at least the speed, and the height of that position, or the stretching of the spring, without knowing how the object goes between position 1 and 2. So if I, for instance, had an object that starts up here, comes down, does a loop-de-loop, and ends here, and I want to know what the velocity is here at position 2, if we use Chapter 2 equations, I'd have to know, like, an equation, a path for that loop-de-loop. But if it's only conservative forces here, I can just say that the mechanical energy at position 1 is equal to the mechanical energy at position 2. So that all I need to know is what that change in height is and what the initial velocity is, or speed is, excuse me, and I can figure out what the speed is at the bottom. I don't have to know what happens in between. I just need to know where I ended and where I began. Okay, makes sense? Okay, so let's do a bunch of problems, make ourselves feel better here. So the first one I want to do is page 203, number 18, which is a continuation of the problem that we were doing last week. That would be great, Elisa. Thank you. Now we need to know what the numbers are, right? So L is 2 meters, theta is 30 degrees, and M is 5 kilograms. Okay. So if you remember the problem that we did last week, that was number 7. We had a pendulum of length L with a bob of mass m at the bottom. And we pulled it out an angle theta. And then we let it go, and we figured out some things. I think we figured out what the change in potential energy was. I think we figured out the work done by the gravitational force. And now we actually want to know what the speed is going to be at the bottom. Okay. So what's the force that's responsible for this object moving? The gravitational force. Is the gravitational force conservative? Yes, the gravitational force is conservative, which means that I can use the conservation of mechanical energy. So I'm going to let my release point be point 1, and the lowest point in the swing be point 2. So because it's a conservative force, I can say that the mechanical energy at point 1 is equal to the mechanical energy at point 2. And so we're going to have a kinetic energy at point 1, a potential energy at point 1, a kinetic energy at point 2, and a potential energy at point 2. And those potential energies are going to be gravitational potential energies. All right. Now, as in every kind of problem we do, we have to have a point where x or y, depending, is equal to 0. So where should we let y be equal to 0? Here? Here. 1 or 2? I'll let y be equal there. Okay. If y is equal to 0 there, then the gravitational potential energy is also equal to 0 there. Okay. You with me? Okay. So, is my object released from rest? Yes. So that means that here at point 1, the speed is equal to 0 as well. Okay. And then the object falls a height h, right? And if you go back in your notes, what was h equal to? Thank you. Okay. Are we going to let positive y be up or down? Okay. It would have, but we've set it up this way, so now we're stuck. Okay. What's the formula for kinetic energy? 1/2 mv squared. And what's the formula for gravitational potential energy? MGH, okay. If we assume that there's some 0 point, and actually I'm not going to call it MGH, I'm going to call it MGY, because we're going to let where y is equal to 0 be where UG is equal to 0. Okay. So if I look at this, if up here at position 1, V1 is equal to 0, what does that tell me about the kinetic energy? It's 0. What's the gravitational potential energy at position 1? 0, because that's where we set it equal to 0. Okay. What am I trying to find in this problem? The velocity at point 2. So I'm going to make this kinetic energy at point 2 then. Well, hang on. Okay. And then the gravitational potential energy at position 2 is going to be mgh, where h is equal to L times 1 minus cosine theta. Okay. So I've got 0 is 1/2 m v2 squared plus mgl 1 minus cosine theta. What can I do here? Sort of. I can cancel out the masses, and I can bring 1 over to the other side. So I've got negative 1/2 v2 squared is equal to gl times 1 minus cosine theta. Well, you know I don't like to do it that way. Yeah. Priya, I think you've totally messed us up here. I'm very afraid, and I don't scare easy. Okay, so this is going to give us v2 squared is negative 2gl times 1 minus cosine theta, or v2 squared is 2gl times, yeah, Priya, you've messed us up totally. Yeah, we should have just had this be where y was equal to 0, but no. I don't know what you did, Priya, or what we did. This was supposed to be the easy problem where we just plugged and chugged and we all played with the equations, but no. You're going to get a negative value. You're going to have to take the square root of a negative number. Because this cosine theta has to be less than 1. That's just the way it works. So you're just going to have to take the absolute value of that. Darn it. I think the problem is that y needed to be positive going up. I think that's what the problem is. I think it's this, that we should not have done that. But I was trying to salvage the situation. So we're just going to take the square root of that. What was L? 2 meters. Okay. I cannot encourage you strongly enough to make sure that you're writing in your units. There were a number of problems on the Chapter 7 Part 2 homework where people weren't writing in units. So you decided it didn't really matter whether it was centimeters or meters, and you just left them as centimeters and then made up units and things. It was not pretty. Okay, so please make sure that you're writing in the units so you can tell whether or not they cancel. What'd you get, Priya? Yeah.
So that was the answer?
That is the answer. But no. I really think the problem was when I let positive be down. I don't think I should have done that. I think that was the mistake. Okay. Would you like to go to the nurse's office? Okay, then let's not talk about it until there's a bigger problem. All right, so let's keep going. We'll do a couple more problems and then I'll give you a break. So let's do one with a spring and gravitational potential energy. So let's do page 204, number 24. And we're not going to let Priya choose where y is equal to 0 anymore. I'll be in charge of that. All right, somebody read it, please. Okay, so let's start with a picture here. So here's my spring sitting in its natural length. Actually, I'm just going to make this picture bigger, that's all. Here's my spring sitting in its natural length. Here's my object of mass m equal to 2 kilograms. And what's going to happen? I'm going to let go of the mass, and what's going to happen? Maddie. Okay, so it's going to accelerate, it's going to hit the spring, it's going to compress the spring. Okay. Now, let's talk about this in terms of energy. So when my object is hanging up there, held in my hand, what kind of energy does it have? What kind of potential energy? So it's got gravitational potential energy. And what happens to some of that gravitational potential energy as my object falls? It's converted to kinetic energy. Depending on where we let y be equal to 0, it's still going to have some potential energy. And then what's going to happen when my object hits the spring? What's going to happen to the energy? What kind of potential? Elastic potential energy. But where does that elastic potential energy come from? It can't just appear out of anywhere. Remember, what's going to happen to the object after it hits the spring? What's it going to do? Well, we know the spring is going to compress, but what's going to happen to the object was my question. It's going to slow down, which means what else is getting smaller? The kinetic energy. So some of the kinetic energy that the object has when it hits the spring is going to be converted into elastic potential energy. Okay. We're going to let this height here at the relaxed length of the spring be equal to 0. And that's because UG will be equal to 0 here, and U spring. Okay? And I'd like to draw this situation again so that we can really talk about the energy. Okay? And in fact, you know what? I'm just going to go to a different slide. Okay? So here's going to be the ground level the whole time. Here's my initial condition. When my mass is just hanging out up there. Okay? So this is situation 1. And remember, this height here all the way across is going to be y equals 0. So what kind of energy does my system have here in situation 1? What kind of potential? Yep, it's all gravitational potential energy. My object's at rest, so there's no kinetic energy. Okay. The second situation I want to talk about is when the mass just lands on the spring. What kind of energy do I have here? It's all going to be kinetic because my block has come down to where the gravitational potential energy is equal to 0, and I don't have any elastic potential energy yet. Okay. My last situation is where my spring is at its maximum compression and the object momentarily comes to rest. So what kind of energy do I have here? I've got elastic potential, and what else? Gravitational potential energy. If I'm not at my y equals 0 line, I have gravitational potential energy. It's going to be negative in this situation because it's below the line, and as we talked about after the problem with our last problem, we need positive y to be up. Okay, so I can take any of these two situations and set them equal to each other. Because the total energy, the mechanical energy at all of those situations has to be the same. Because it's conservative forces that are making the transfers of energy. What kind of forces are responsible here? Gravitational, that's conservative, and what else? A spring force, and that's conservative too. So, and the system's closed as long as I include both my mass and my spring and the Earth. Then it's a closed system. Got all my forces are included there, and we're good. Okay? So, let's back up a minute, and what are we supposed to find? Okay, so let's bop up here for a minute again. And let's call this distance y1, and this distance, y3. And then what I'm trying to find is what? What am I trying to find then? If I'm trying to find the maximum compression of the spring, what variable is that? Y3. Okay. So if I want to find Y3, which two of my positions should I be comparing? Well, we definitely have to have 3 in there. I would do 1 and 3 because I know what this Y1 is, right? Aren't I told how far above the spring my block is? Which means I know what the gravitational potential energy is. I'm trying to find Y3, which is going to play a part in both of those terms. But what I know absolutely nothing about is that kinetic energy. So as much as that would be nice and easy, I'd have to figure out what it was first. Okay? And remember, the whole point about using conservation of energy is I can compare any two random positions. Not random. Yeah, they can be random as long as they're all part of this system. Okay? So I know from my picture up there that at position 1, I've got gravitational potential energy 1, I'm going to call it. And at position 3, I've got spring potential 3 plus gravitational potential energy 3. Okay, you with me? We good? All right. So, what's my formula for gravitational potential energy? mgy. So, when we're talking about position 1, it's going to be mgy1. What's my formula for elastic potential energy if I let y equals 0 be the relaxed length of the spring? Nope. Nope. I want to know, how am I going to write the elastic potential energy here? Elastic. Nope. Remember, the elastic energy, it doesn't matter whether it's positive or negative, whether it's above or below the, there we go, thank you. And in this case, it's going to be ky3 squared. Okay. Yep, plus mgy3. Okay. So, we know everything on this side, right? We know what K is. We know what mg is. But what I don't know is y3. So I've got 0 is equal to 1/2 K y3 squared plus mgy3 minus mgy1. But remember, this is just a number. So, what am I going to have to do to find y3? Maddie. No, because I don't have one in every term.
Can't you energy y path and then factor y squared or
What are you going to have to do? What is this? What kind of equation is this?
quadratic?
It's a quadratic. It's a parabola. Okay? It's just hidden in there. So what are your options for solving a quadratic? What is it, Gianni? What? You could graph. Okay. Graphing would probably be better. What's your other option? Quadratic formula. Okay, which is the way I did it, but I would recommend graphing because it took half a page and it was nasty. Okay, so remember, these are all numbers. So what was K? 1,960 newtons per meter, Y3 squared. The mass was what, 2 kilograms times 9.8 meters per second squared Y3 minus 2 kilograms, 9.8 meters per second squared times what? Point 0.4. Thank you, Gianni. Because it was 40 centimeters, but we have to convert it to meters. Okay, so if I were you, what I would do is I would do all the math and have some number in front of y3 squared plus some number in front of y3 minus whatever that is. And then, yeah, I'd plot it in your calculator and figure it out. And remember that you should have two answers because it's a quadratic. And I'll fill these in. That was kind of weird. Oh my, there's something wrong with this calculator. Something terribly wrong with this calculator. Oh, yeah, it is. Oh no, that's not what I want. I want that. That's what I get. But which answer is right? Think about the problem. Why would it be the negative one, Maddie? Yeah, because if we look back up here, y3, which we labeled on our picture, is negative because positive y is up. So what we're looking for is the negative 0.1 meters. So my answer is actually that y3 is negative 0.10 meters. Okay? All right, so we'll take a break here for 2 or 3 minutes, and then we'll come back, and I've got another problem and something else for us to do.